Good morning, everyone. Well, I want to thank Nex and Celeste for all the work organizing this workshop and for having me presenting some of the work we are doing within ACI 549. So I'm going to have a pretty long background, actually, because this is basically what we are trying to do in ACI 549, and to understand that, it is important that I can explain where we are right now. So I think most of you are familiar with FRCM and SRG, but in case you're not, these are composites basically similar to the more probably well-known FRP, where there is fibers typically in the shape of a mesh, unidirectional or bidirectional, that are embedded in inorganic matrix. This can be cement-based, lime-based. It can also be a geopolymer. We have tested several of them. And the idea is there are some applications where we're looking for a really good compatibility with the substrate, especially if there is moisture. The inorganic matrix is not as influenced by temperature and humidity as the FRP. It's fairly easy to install. And it can be used for strengthening, but also there are a lot of cases where the concrete cover has been removed because it was damaged, and so it might make sense to have a thick layer of a cementitious mortar with the fibers embedded. So it can be also used for repair. As always happens with these composites, the main issue is the shear transfer. And in terms of testing the shear transfer, there is a lot of different tests. This is a well-known paper from the early 2000s where there was a description of all of them. And the single lap, which I'm going to be talking about today, is one of them. So it's basically a test where you have a block of concrete or masonry, the composite apply on one face, you restrain the block, and you are trying to pull off the composite. So this is the long background. So what are we doing in ACI 549, 620, and 420, which are the two documents that are the guide to design FRCMs for concrete and masonry. So the ACI requires that we use a tensile test of a coupon made of FRCM or SRG. And I actually didn't mention SRG. It was defined there. It's the same, but the fibers are steel. And the idea is to pull this coupon to get some properties that then are used to design. And in particular, from this test, ACI basically determined the strain and the elastic modulus to use in the design, typically in the cross-sectional design. So we need to acknowledge that these composites are a little bit different from FRP, because in FRP, we never typically see any issue between fibers and matrix. So the bond between the fibers and the epoxy resin is usually good enough that usually it's the bond with the substrate the problem. But in the case of FRCM and SRG, the bond between fibers and matrix can play a critical role. So the goal here is to understand how we can really improve the design, but really considering whether or not the tensile test that is currently used makes sense for determining the properties that then we're going to use in design. So this is a classical picture of the test used in ACI, which reference AC 434 document from ICC. And the idea is you see engraved the coupon with the fibers in the middle of the thickness, and then you glue two plates at each end, and then using a Clevis type connection, you're pulling basically the plates through bond transfer to the matrix, and you're obtaining your response of the tensile test. This is a typical response. You have initially the cracking of the mortar, and then eventually the fibers will pick up the load. So here is the key point. The ACI tells us that to determine the strain and the elastic modulus, for the elastic modulus, we're going to take two particular values of the stress corresponding to a percentage of the ultimate stress, and two corresponding value of the strain. We're going to determine the slope, and that is the elastic modulus. Then the strain that we're going to use for design is basically related to the strain at a certain percentage plus 40% of the stress, the maximum stress, divided by that elastic modulus of the composite. And eventually, again, the effective strain is basically the epsilon FU that I just talked about minus the standard deviation. And from that, and the elastic modulus, you can get the stress of the composite in design. So if you do your calculation, 0.4 FFU, you get the horizontal line. Then you take 0.6 FU, the epsilon, and you follow the second equation of the epsilon. You will see that this is the epsilon FU. And if you basically multiply by EF, this is the effective stress that you're going to obtain. Again, here the goal is not to go through the calculation, but it is to show you what the ACI will get you in terms of the stress and where your response is for this composite. I should mention that in any of these tests, regardless of how long the coupon is, the first thing you see is two cracks where the plates are, and then depending on how long the free part of the coupon is without the plate, you might see one in the middle, two more, and so forth. So what we have shown is that analytically, we did a little bit of work with my colleague, Professor Dantino and Professor Focacci, that the clevis type top part basically is nothing more than a single lap bottom part, where the plates, the steel plates, act as the substrate, and basically the section where you have the crack in the matrix is the end section of the single lap test. So really what you are testing is a single lap test, and all depends on the length of the plates. Typically, in this composite, you need a fairly long length to achieve the entire transfer length. And so the problem is, this means that your plates need to be fairly long. And if you don't do that, you're not going to achieve what is the potential of this composite. So again, in summary, the bonded length of the plates acts as the bonded length in single lap test. Okay, and the other key point is that, again, this can be easily proven mathematically. The length of the free portion, L sub t, basically determines how many cracks you have, and because the strain is measured over the free part, it will give you different values of the strain. So in other words, if we test the same composite with different length of the plate and different length of the free part, let's say 3 different configuration, we will get 3 different of these responses, 3 different values of the strains, 3 different values of the elastic modulus. So this means that this test, as it is, unless we prescribe something more, will not basically give us a unique value for design. And so this is not probably ideal. We have proven, and I don't have time here, we have proven that if you do correctly the clevis type test, you actually get exactly the result of a single lap test, properly done. The issue is, again, it's fairly long, and also if you do a clevis and not a single lap, you will never know if your composite bonds well to this substrate. You only know what happens to the composite. And there are cases where the composite doesn't bond well. It might be it needs more surface preparation, and so forth. So these are some picture of some tests. We have done a lot of them. So now what we're proposing in 549, we're saying, okay, let's do a single lab test, which is actually what the European guide prescribes to determine the property for design. It's a fairly simple test. There are, again, other configuration. This is easy because you can manage the block fairly easy. My students usually can lift it. So again, it's a block of concrete or masonry where you apply the composite. And we prescribe also some details on how to prepare it to make sure that your fibers are in plane, there are no secondary effect, and so forth. I want you to note that the fibers are bare outside the bonded area. So you use the matrix to bond the fiber for the length that you want to test, but then the fibers are bare outside. And the reason for that is in this picture. So if you're familiar with FRP, whenever there's going to be a flexural crack in a beam, the crack will then determine a propagation at the interface with the FRP. You see here at the bottom. In FRCM, because the matrix cracks with the concrete, what you're going to have is that you have the crack continuing into the matrix. So it's the fibers, the actual carrying, loading item in the cross-sectional analysis, not the FRCM. So here you see some of the picture of the actual ACI 549 documents that we are balloting right now with all the details. There are LVDTs to measure the slippage of the fibers. There are LVDTs optional. You see them here in the back. You can measure the undesired rotation backward of the specimens, which will give you, again, an eccentricity, so an additional peeling mode. So there are a lot of things that can be done to control your results. And then we provide in the guide a list of all the potential failure of all the composites that we tested over almost 20 years with the FRCM and SRG. So you could have the slippage of the fibers, very common when the fibers are not coated. You can have the interlaminar failure, meaning B, the fibers will slip, will drag with the fibers the top layer of the matrix, and you create basically a shear crack, interlaminar crack at the interface with the bottom layer of the fibers. You can have the typical cohesive failure of FRP. The entire package debonds from the substrate. You can have a clear debonding of the package. So in other words, it debonds, but there is no cohesive failure. So the package is fairly clean and the surface is still undamaged of the substrate. You can also have failure of the fibers if the bond is really good, and there are composites that they do that. Or you can have slippage and then at some point failure of the fibers inside the matrix, and this depends basically on, again, the nature of the matrix and how this bond is, if there is a mesh in the transversal direction, and so forth. So how do you design? Well, you take your Pmax or Pdeb. You see two symbols because, again, we need to understand if there is a cohesive failure, so there is a plateau, or there is a simple max. But basically, you take a value, a maximum value of your load from a single lab test, and then you divide it by the elastic modulus and the area of the fibers to get your strain. So basically, there is no additional working on the response of the single lab test. And again, it's because at the crack cross-section, the fibers are the one acting. I want to mention that what we really should prescribe, we are not at that stage, is that the elastic modulus is not the elastic modulus of the manufactured fibers, but it's the elastic modulus of the mesh. Because testing one fiber or testing a mesh is not exactly the same thing.
One more minute.
Yeah, I'm actually done.
Okay.
So these are pictures of all the tests we have done. It can be used also to the right to do some conditioning, like salt attack, Actually, the FRCM are very happy with salt attack, not the FRP, because it's a porous material, so the salt actually decreases the porosity of the material. And I want to finish with this slide. This is where we need to do some research for 549. In FRP, the strain over a single lap can easily be 3 times less than the strain in the beam when you do design because of the effect of the curvature and the presence of multiple cracks. In FRCM, you can go from 1 to 1.5 the strain on a single lap, and that depends on each single material. So we cannot use a single coefficient. The issue is when we did this analysis of all the database, there were only not that many beams 7 years ago. Now there is more material, and we probably should test even more of these. So again, to conclude, singled out test allow to determine the bond properties of the composite, also considering the substrate. And the goal in the end that we have in 549 is to ballot and publish this single lab test so that then we can use it to modify the ACI document to design the FRCM. Thank you so much.